what the relative thing is what this would look like, or what this would feel like if it hit you in the face. Okay, all right. Now, if you're running away, you're running with it, just like a ball. It's not going to hurt as much. It's not going to have as much energy. Okay, if you're running to it, you know, they're both running towards each other. You're going to have more energy. It's not that the light has more energy. It's you're adding you and the light together. That's the new energy. That's why you think it's blue and it has all this energy. It's not that it has that energy. It's just that when you are adding your energy to this energy. The green guy doesn't add any energy. He's just standing there. The red guy, he's moving with the thing. So his energy is going to be less added to the. You know what I mean? It's not that. It's just like when I throw the ball at 3 different people. One coming towards me, one going away from me, and one just standing there. I throw the same momentum, same everything. It isn't that the ball changes. It's the frame of the person you're comparing the ball to. If the man's running towards the ball, like this, you're going to get more energy. The man's running away from the ball, you're going to get less energy. The man's just standing there, you're going to get energy somewhere in between. It's not rocket science. It's not the photon doesn't change its. We're all not in different universes, and lengths contract for one person and not the other. These are just length contraction is just a perception. Your perception is contracted, okay, and that's just like this. Your perception has changed. That's all. Your frame of reference changed, and now you're adding energy to this red thing. The red thing. It's not changing. You're the one that's changing the energy between you and it. It's like it's not magic. Okay, stop saying it's magic. You don't know why it's happening. You know exactly why it's happening. Okay, it's because if you run towards something when someone's throwing a stone at your face, it's going to hurt more than if you just stood there, and it's going to hurt the least if you're running away. Okay, I can't believe I have to tell people when someone throws stones at you, you run away, it's going to hurt less. You think a 3-year-old would know that, but apparently these. All right, there's only one equation we really haven't talked about, and that's the main equation that we started with, right? This big one. But remember, that's a lie. They're using little p. You have to put big P in there, right? Little p is just momentum, mass times velocity. Big P is mass times velocity times gamma, right? So that changes your formula. This is the formula you need to use. If you don't use this and you use this up here, the equations won't come out right. It doesn't work out. Trust me. I've like 7 pages trying to put this all together. This is the way it is. Okay. This is okay. And what is? I want you to understand. Okay, we're done with the equations. I want you to understand what like rest energy is, or rest mass, whatever you want to call it. This is the energy that you need to stand still relative to space-time. And what do I mean by that? It's the energy giving you the ability to stand still in a gravitational field. You know what I mean? To stand still. Okay? If you don't have that rest energy, okay, it's a certain type of energy. And if you don't have it, you go 186,000 miles per second. It's that simple. Okay? But if you have it, now you can stand still. You have the ability to stand still. Alright? And the next thing I wanted you to realize, right, is like when this guy kicks this ball or throws it, you know what I mean? These 2 guys have to be in outer space. The ball's just floating there. This is on Earth. The guy hits it, kicks it, whatever. The ball in all situations has a potential energy. Remember when we said that potential energy or rest energy plus the moving energy or kinetic energy that you give it adds up to the total energy, yeah? But I want you to understand, and that's true. I'm not saying that's wrong. That's definitely 100% true. But I want you to think of it like this, okay? Like say this ball here is just standing there, all right? You have to apply that. You have to add kinetic energy, not to move it. I mean, you have to do that too, but you have to first give kinetic energy that is equal to overpower that potential energy that you have, right, in the ball. So it's not that you're adding up potential energy and kinetic energy. You're adding up kinetic energy and kinetic energy. You know what I mean? One kinetic energy is what you give to the ball, right, just to overcome, just to be equal to the energy that that ball already had, right? You have to go opposite to that opposite of that energy. You know what I mean? Boom. Then you got the other kinetic energy that's the moving, to get the ball moved after it's already, overcoming the potential energy. That's the way I think. I mean, either way is correct. I'm not saying it's not potential energy. It is, but think about it. You're adding these up to get total energy of what you put into the system, what you put into the ball. And what you put in was enough kinetic energy to be equal to the potential energy that the ball already has. The ball has potential. It has potential energy to not move. Okay, and you have to overcome that by giving it kinetic energy. Then once you do that, now to actually move it, you have to give some more kinetic energy. All right. Now let's think about what's this say? If you don't have rest energy / mass, space-time would force you through it at 186,000 miles per second without using any force. Okay, just like gravity. But let's get up here on this picture right here. Let's say you're in outer space or whatever. Your hand comes, it's coming from this side to this side, and it's going to smack this ball so it goes to the right, right? See, you think that you think the hand hits the ball, and then the ball, and that's what accelerates the ball is the hand. That's not happening. Okay, that's BS. Okay, so you have atoms in your hand, and there's atoms in that ball, and atoms don't touch each other. Okay, so you can't touch the ball. Okay, but once you get close enough, right, your atoms have EM force, fields around them, right? The ball has atoms, so there's EM forces there, or EM fields there too, right? When your EM field gets close enough to this EM field, they react. Yeah. And guess what they do? They make a whole bunch of freaking photons, man. Heat, infrared, that's photons, information carriers. See, acceleration can't take place without information carriers. Okay? Anything. All force carriers and information carriers move at 186,000 miles. Most, if not all, are photons. Okay, so you never touch the ball or anything ever in your entire life. Your EM fields touch and react, producing photons, right? And that's the force you feel. Like when you hit the ball, the hand's going to feel force too, and the ball's going to feel force because it's throwing out photons. That's what the hand feels. It feels the photons from the ball. And the ball feels the photons from the hand. You know what I mean? The photons give the information and the energy, mass, and the momentum, and the velocity, and the acceleration to the ball. This is where the acceleration or all the mass, where'd the mass come from? From the photons. They came from the photons. They add to the energy or they add to the mass, whatever you want to call it. Okay? And it's all about, it's all time dilation, acceleration, everything is about photons. And this type of transfer of information. Okay? Why can't you move as fast as light or faster? Okay? Well, think about it, right? Look at this hand up here, right? It's going to hit the ball, but it doesn't really hit it, right? It just reacts, gets close enough. The EM fields react, throw out a whole bunch of photons, right? Well, the photons are the ones that are actually hitting the ball, making the ball. But the photons are what are accelerating the ball, the information carrier. Okay. Now, if the information carrier is the photon, and let's say the ball is already moving at the speed of light, you know what I mean? How can the information carrier tell the ball to accelerate more when the acceleration when the thing trying to give the information can't go fast enough to give it to them, right? Like this ball's going at its speed of light. How does it catch up to give the information? Hey, accelerate, ball. We want you to go faster. You can't. The information carrier, you'd have to have an information carrier that was going faster than the speed of light to catch up to the ball to tell the information. Okay? And the last thing is, see down here? I can only throw a ball, say 100 miles an hour, okay? See this little dude, he threw a ball, it's coming this way, right? To the right. So I can only throw, if I can only move my hand at 100 miles an hour, how could I make the ball go faster than 100 miles an hour? You know what I mean? Even, I can't do that. I can't, because the thing that you're using to accelerate another thing has to be able to actually go faster than it wants the other thing to go. You know what I mean? If I want the ball to go faster, then my arm needs to go faster. Just like this ball up here. If the ball can't go faster than the thing that's going to hit it and make it accelerate, right? Go faster. It can't go faster than the thing you can't. The ball can't go faster than the thing's trying to accelerate it. If the hand can only go at the speed of light, how can it catch up to the ball? Can't do it. All right, the very last thing. Why do they say this lie? You know, the faster you go, here's 0.5 C, 0.75, blah, blah, blah. They say that your mass gets so big, it's just infinitive. Oh my God, we don't understand. It's so complicated. This goes back to throwing stones at you. If I throw a stone at you and you come towards me, you know, hey, it's going to hurt more than if you're running away. Now I want you to see this smiley face, this ball. He's going this way arrow's saying, right? He's going 0.5 C. Now, if these things are the ones that are pushing, telling the information, doing the accelerating, right, and they move at a specific set speed, C, right, when you're standing still and you get hit by them, then they're going to punch you in the face and they're having the full force. But if you're going at 0.5 C in the same direction they're going, just like a ball, me throwing it at your face, if you're running away, it's not going to hurt as much. Right? So now here, it's only the difference is 0.5 C. See, here the difference is 0.25. See, it's not that you're getting more mass, it's just the thing that's accelerating you, okay, has a set speed. And if you keep speeding up, then the speed, when it hits you, then the energy it can give you is going to be smaller and smaller and smaller. That's just common sense, you know what I mean? The faster you run away from my stone that I'm throwing at your face, the less it's going to hurt. What's so hard to... Okay, so once you're at 0.5 C and you're only getting this little bit of energy, you're only getting half of the energy you would get at, say, you know, standing still or whatever, you know what I mean? Here, you see here, you're already gone to like, oh, I raced it or whatever. What was that? Probably 0.01. Oh, 0.01 C. Yeah. The energy that you would give to this ball at this point, none of it would actually... They're both moving at the same speed. You know what I'm saying? It's like I can't... If the ball's going and I'm at 100 miles an hour and my hand only moves at 100 miles an hour, I can never catch up to it. You know what I mean? Even if I'm slightly faster, but if I'm only slightly faster, I give less energy. So it's not magic. It's not a mystery, okay? This is just throwing... All these woke physicists need to come to my house so I can throw stones at them. And we'll do some research, and they can see that it's not about this, you know, this thing getting more mass. It's that the energy transfer is going to be less. You can't... If you're going... Come on, man. This is ridiculous. They make it out to be some kind of mystery. It's no mystery, man. It's just Common sense.